Welcome to this session called Data Science for Biomedical and Healthcare Applications. I am Paul Cherukuri, the Executive Director of the Institute of Biosciences and Bioengineering here at Rice. Please join me in welcoming our first speaker.
I should first introduce myself. I'm a PhD student from School of Biomedical Informatics, UTHSC, and today my topic is computer-aided diagnosis of dermoscopic images using the deep learning algorithm. First, my presentation are going to have three sections. The first is to help you learn the method to apply the deep convolutional neural networks to a real-life hospital setting skin disease database. And the second part is going to analyze the misclassified causes and to develop method to actually trying to improve the accuracy of computer-aided algorithm. And the third part, I'm going to introduce a little bit of our ongoing work. So first, I'm going to introduce our data set. So our skin disease images are coming from a hospital. That's the Department of Dermatology, Peking Union Medical College Hospital. And the total database contains over 28,000 skin disease images using the MoMax HD #1 dermoscopic device. And also we create the golden standard for each image that I'm going to introduce later. So we actually have three separate experiments using three different data sets. So for data set A and B, the only difference is that we kind of wanted to test if there is any influence of the uneven distribution of the image and their different category. So the data set B is kind of just we extract the same amount of images from data set A is kind of weak. Yeah. Okay, so we extract the same amount of images from each category, that is 132, to run for a experiment B. And for dataset C, you can see the amount of images that we use together improved a lot. And also, there's another difference that we are not only using the psoriasis as the first category. Instead, we put the psoriasis along with some other multiple diseases together as the others group. And the reason we do that is because we wanted to apply this algorithm in a real-life situation. So when the user uploads an image of himself, we want to give a return no matter what kind of disease the patient is uploaded or the doctor. So here is the structure of the cutaneous diseases, and there are three main kinds. And I also put the position of the disease that we actually use in our experiment. So the psoriasis belongs to the first main kind of skin disease. And the SK, also the melanocytic nevus, they belong in the same benign kind. And also the basal cell carcinoma is under the malignant category. So the reason we choose those four diseases as our in our experiments is not only because they're the most commonly seen skin disease in hospital, also because they're representatives of the two main binary classification situation. One is the representative for the most commonly seen skin cancer disease, and the other is represent for the most studied skin disease. And here I'm going to introduce the annotation process that we use excuse me, to create a golden standard for our each input image. So each image are going to be first reviewed by two experienced dermatologists, and they will discuss, and if they reach the same agreement, then we have the final annotation for our each image. But if they disagree with each other, we will have a third dermatologist involved, and they will have a discussion. And if after discussion they agree with each other, then great, we have the final annotation. But if not, we are going to take further biopsy examination for that specific patient to make sure. And for all the images in our data set, we divided them into training, validation, and testing set using the ratio 8:1:1. So the reason we separated the validation set from the training set is because we want to prevent the overfitting problem that is pretty often seen in the machine learning domain. So we also use the 10-fold cross-validation just to lower the variance of our algorithm. So the 10-fold cross-validation process is shown in this graph that we have 10th iteration, and all of the images are divided into 10 folds. And as I said the ratio before, so all the yellow cubes represent for the training set, and this green one represents for the validation set, and the purple one is the testing set. So for each iteration, the position of the fold of different side is also rotating. So to make sure that for each iteration, we are using the different folds for different set. And here I'm going to briefly introduce the model structure and features of our algorithm. So the deep learning algorithm that we use is actually the GoogleNet Inception version 3. Because our image is not like a large data set, it's actually pretty small. Only have thousands of data, no more than 5,000. So we just adjust the final layer. So it's actually also kind of a transfer learning because the original architecture was trained based on the ImageNet database. And ImageNet, I'm sure you are pretty familiar with, is trained based on over millions of images and over 1,000 normal life objects. And we here transfer learning into the skin disease domain. So for each input image, it's going to go through 3 main kinds of layers that are convolutional layers, pooling layers, and fully connected layers. So the convolutional layers and pooling layers actually combine together to form into kind of a feature extraction method that are, I believe, is the most advantage part for deep learning to make it better than the traditional machine learning algorithm, because the feature extraction actually did a pretty good job. So the convolutional layer actually used the filter matrix to extract the image matrix for useful information. And after the convolutional layer, we are going to downsample our image by using the pooling layer. Here we use the max pooling. So this downsampled method can also help to reduce the memory consumption and save more space for the convolutional layer. So after repeated this pooling and convolutional layers for several times, all the extracted features are going to combine with each other and serve as in the classifier in our fully connected layer. And also we are going to apply a softmax layer before the final output because it can transfer all the outcomes into a probability value to do our classification task. And here is the evaluation and the results of our algorithm. As you can see, the average accuracy is coming from the 10-fold cross-validation. For dataset A and B is actually pretty similar. So that's also kind of proof that the uneven distribution of the image under different category actually doesn't have a huge influence on the computer algorithm's accuracy. And also, we can notice that for dataset C, even though the number of images for training improved a lot, but the accuracy actually dropped. But remember that we use different category setting for dataset C. The first category actually contains multiple different skin disease, and we believe that is the reason why the accuracy dropped. But it is also theory proof that after we improve the number of input image in the training set, the standard deviation for dataset C semantic dropped from 3 to 4% to 0.8%. And that is pretty obviously dropped. So we also calculated the precision recall and F measure for dataset A, and the AUC and specificity and sensitivity for dataset C. And here is the ROC curve that I created. We can see that for BCC, it actually have a larger AUC score than the SK group. So we are just wondering like why some of the group have a higher accuracy than the others group while they're training together and even use the same number of image for training. So that is bring out our second session that we want to analyze the misclassified causes and to develop methodology to improve the computer-aided algorithms accuracy. So here is actually the semantic error analytics that we did. There are two informaticians and two dermatologists involved. And we created 3 main causes of the misclassifications. And those are all a summary based on our discussion of specific images from the misclassified results. So there are 4 main kinds. The first is the characteristics of disease and also the multiple diseases that represent for maybe there can be several skin disease lesions but lie in the same image. And also the interference factors such as the hair, the line, air bubbles, or dermoscopic gel, also the brightness and balance. And the 4th kind is obviously the accuracy of the algorithm itself. So I'm going to further illustrate. So here's a detailed explanation of the error analytics. So for figure 1, we can see that it's actually psoriasis, but was misclassified. So the typical features of psoriasis are not shown in this figure. It's kind of the typical features of psoriasis, such as the dotted blood vessels are significantly reduced. So we categorize this under the type of atypical characterization. And for figure B, is actually a special type of BCC. So this image is annotated as BCC but was misclassified. So this is actually a not usually seen features of the BCC disease. And we believe that is the reason why the computer algorithm didn't recognize it. And for figure C, is the multiple diseases because there are both SK and BCC lies in the same picture and was classified by the algorithm to SK. But you can still see the BCC lesions in the image. And for figure D, it's pretty obvious that hair is kind of blocking out, blocking the lesions of the diseases. Through our research process, we actually discovered that the dermatologists usually give their diagnosis based on more information than just the image itself. For example, the age of the patient or the gender of the patient. And there are studies showing that a particular amount of sunshine exposure to body part can increase the risk of having BCC. So those semantic features cannot be seen in the image itself. So we are wondering why we can't combine the semantic features, or to say the clinical knowledge, into the process of deep learning for the computer algorithm to have a better performance. So we bring out, based on our semantic error analytics we did before, we bring out this semantic hierarchical structure, that the way we want to combine the semantic features into our deep learning algorithm. And so first, we are going to expand the type of our image, not only limit to the dermoscopic images, but also the histological image, also smartphone images, so patient can use them at home. Also, the pre-processing technique based on our error analytics we did before. So we are going to combine them together as a total input vectors to the deep neural network algorithm. And we will have the final diagnosis or classification results that can also help us to improve the selection of our semantic features. So we know which feature is good for the training, which is not. And also, we did a task that's kind of to test the performance of the computer algorithm against human. So in this task, in this computation, we have a data set that is separate from the training, validation, and testing set, consistent of 70 images of those 4 groups. And the performance of human, we have 174 trainees that have experience in dermatologist diagnosis, and they have the average accuracy of 78.96%. And for our computer algorithm, we have the overall accuracy of 80%. So we can see that a computer algorithm actually did a little bit better than human. Also, the application part. So we are developing the app that combine our algorithm with a little dermoscopic device. So for the hospital setting, the doctor could use such device to help aid their diagnosis. And also, patient could use this kind of app or device at home to have an early diagnosis. So we believe this kind of algorithm, if we develop it into clinical setting, it could help the education resources distribution in all of different countries in the world. So this third part is our ongoing work. That this kind of deep learning algorithms are not limited to just the skin disease domain. I'm going to introduce the preliminary work that we did using the chest X-ray images, but the same algorithm. So our ongoing work, first we are going to enlarge and expand the data set. Just as I explained before. And also, we are going to embed the semantic features into the algorithm. There are studies that have been done, but we should still keep looking for more powerful and meaningful data that's actually related with the disease itself. And also, to generate reports or description based on the clinical image. And I'm going to show an example that's already been done, but the accuracy still needs to be improved in order to actually use in the real life. And also, we are going to develop the knowledge-based disease inference system that we use the relational database to consider into our deep learning algorithm. Our overarching goal is to develop a clinical decision supporting system. So here is the example that we use the same algorithm to classify the chest X-ray image. And we actually tried out kind of like combination of different features from different deep learning algorithms. And here is the example of how we are going to generate reports based on the clinical images. So the first row is the real-life chest X-ray image from the hospital, and the second row is the actual reports, original reports given by the radiologists that they actually wrote themselves. So the third row is the generated report by the computer algorithm, but we can see that if you look further into it, even though the structure is pretty much similar or alike, but the accuracy still need to be improved because the content are not like 100% accuracy. So it still need to be improved to actually help the radiologists. So here is an illustration of how we are going to develop this knowledge-based disease inference system. For example, so the content here is not exactly the one that we are going to develop, but to further illustrate, thinking like there are lesions that the computer algorithm returned for a skin disease image. And so the lesions will have features A, B, and C. And maybe even the doctor will rely on the same rule that some certain combination of the features could be used as a reference to have a certain disease X. So this is kind of a relationship that we could use in our inference system. And after we have the disease information. We could also further infer like the treatment plan or the medication plan. So thank you for Dr. Tao and Dr. Tao's lab from UT Health. Also Dr. Liu and Shi Department of Dermatology, Peking Union Medical College Hospital, and thank you for Dr. Li and Shenhua from Washington University of School of Medicine in St. Louis. That will be all for my talk. Thank you.
So I have a quick question about your the results, the accuracy that you got between A, B, and C, sets A, B, and C. On set C, way back at the beginning, you had some really highly imbalanced classes. How did you show that the lower accuracy was not because of the highly imbalanced classes, rather than just throwing everything into the other class?
Actually, if you remember that for dataset A and B, we're kind of trying out if the uneven distribution of the image will have an influence of the computer algorithm accuracy. So actually for dataset B and dataset A is an uneven distribution, B is an even distribution, and the accuracy is not obviously like difference. So we draw the conclusion that the uneven distribution of the image and their different category won't have a large influence on the computer algorithm's accuracy.
And how does this compare with Stanford group, which has developed a system to classify skin cutaneous carcinoma versus normal? Are you aware of that work?
Yeah, so you mean that Nature paper published by Stanford University. So actually, first we're using the different data set. They have like skin disease data set from like several hospitals together. And also they have more kinds of skin disease. So for here, we use, for the dataset A and B, we only have four kinds of skin diseases. But I remembered they have over 100 types of skin diseases. So actually, if you just compare the accuracy, our algorithm actually is a little bit higher than their accuracy, but because the setting for the experiments is different, so I couldn't just compare directly with their results.
It's hard to compare directly. Rather than using 100% supervised learning, have you tried to use unsupervised learning to look if there are rare classes of condition which kind of can be defined as one group? And rather than classify 4 different types of disease, maybe a subtype of disease that can be shown based on unsupervised analysis before applying deep learning algorithm.
Oh, you mean like why we didn't use the unsupervised learning?
Yeah, just look at the distribution of data first before fit them to 4 different classes. Are there some novel conditions which you could actually see from the data?
Yeah, I believe there are studies that actually use the unsupervised learning, but because our data set is not large enough, it's only a small size database. So I think the supervised learning that comes with the gold standard will be more accuracy.
You said you have only about 5,000 images in the training set. Have you tried any data augmentation during the training?
Oh, so we have no more than 5,000, and we try to flip the images. That's kind of an augment of the data set, if that answers your question. Because because the lesions, because we are using the dermoscopic images, so actually the lesions are taking like all of the part of the image itself, so we cannot like crop the image to, because that will like kind of just crop the lesions itself.